Καλημέρα και από μένα. Λέγομαι Petros Koumoutsakos. Είμαι καθηγητής of Computing in Science and Engineering στο Πανεπιστήμιο του Harvard. Τέλειωσα το Πολυτεχνείο, προέρχομαι από την Ελλάδα, όπως πολλοί από εσάς. Και πριν ξεκινήσω, θα ήθελα να ευχαριστήσω μερικούς ανθρώπους. Καταρχάς, τον Βαγγέλη τον Καρκαλέτσι και τον Γιώργο τον Ούνεση από το Δημόκριτο, οι οποίοι είναι μεγάλοι συμπαραστάτες της προσπάθειας που κάνουμε και θέλω να τους ευχαριστήσω θερμά για όλα αυτά που έχουν κάνει για μας. Μετά θα ήθελα να ευχαριστήσω τον Αντρέα τον Μπουντουβί, τον πρώην πρίτανη του Πολυτεχνείου, αλλά τον πρόεδρο του HIAS στην Ελλάδα, ο οποίος έχει κάνει απίστευτη δουλειά για να πραγματοποιηθεί αυτό το συνέδριο. Και μια και μιλάμε για απίστευτη δουλειά, ο άνθρωπος που έχει κάνει την περισσότερη δουλειά από όλους μας και χωρίς αυτόν τίποτα δεν θα ήταν δυνατόν, είναι ο άνθρωπος που βγάζει φωτογραφίες αυτή τη στιγμή, ο Γιάννης ο Τζιγκουνάκης, και θα ήθελα να σας παρακαλέσω ένα μεγάλο χειροκρότημα. Πέρα από καθηγητής του Harvard, τυχαίνει να είμαι και ένα μέλος του board, ο chair of the board για την ώρα, for something that we call Hellenic Institute of Advanced Studies. And if you allow me, I would like to continue now in English. And I think the rest of the presentations will be in English. It's very difficult for some of us from the diaspora to speak Greek when we, in particular, we present our scientific research. The Hellenic Institute of Advanced Studies was formed by several members of the Hellenic diaspora, mostly from people who have been working in the area of physics and engineering. And our idea is to create bridges with our peers in Greece. Greeks, we are not very famous about being united, but I think that when we are united, we can do amazing things. And this is just a small effort to try to accomplish this particular task using science as a way of making a difference to the Greek society and to the Greek science. What is the HIAS network? We have the HIAS members, they are all members of the diaspora. So we have 200 members from over 65 top-rated universities from the United States, the European Union, Switzerland, and the UK, and we are expanding to other places. Many of us are members of the US National Academy of Engineering, Science, and Medicine, and several people, including, for example, Professor Sifakis, who is one of the most famous Greek scientists, being the recipient of the Turing Award, which is the Nobel Prize for computer science. What we try to do is we try to serve Greece by creating a hub for science and innovation for Greece. We are interested, as I said, to create bridges. We don't believe that us coming from the diaspora will come here and solve every problem. I think it's only the bridges and the interactions between the people abroad and the people here that can make it happen. We're interested in developing international collaborations that go beyond Greece. One of the excellent advantages that we have by traveling the world is that we create networks. And these networks can be very, very powerful and a potent and an enabling thing for us in Greece. And finally, we believe in excellence. I think the culture of scientific excellence is something that we experience in many universities that we go abroad. And I think this is something that can be valuable for Greece because I think we are all capable of excellence, but I think it's the culture that is missing sometimes that does not allow us to pursue this excellence. So we hope to contribute to that. So this is about HIAS. By going to the web, you can find all the information that you may want to know about HIAS. So I would like to start my talk. My talk is not going to be so much about my research, but will serve as an introduction to the AI. If any speaker cancels, maybe I will jump in and talk about my work, but allow me to give you a few thoughts, personal thoughts about AI. And I would like to start, of course, as all Greeks do. Of course, we start where it's the favorite place for us, and that's about 2,500 years ago. And to this, which is reminiscent of what I see in front of me right now. So 2,500 years ago, there was the Academy of Plato, and I'm using this picture because I would like to mention a particular story that I think describes the pursuit of humanity in knowledge. So the story is the allegory of the cave by Plato, where Plato says that what we are chained in front of a wall. There is a fire behind us, and what we see is we don't see the real world, but we only see shadows. And then when we see these shadows, each one of us has an interpretation about what is this particular shadow that we see. So some of us call it a dog, an animal, or a pet. And what happens is one day, one of us gets unchained and goes out and sees that the world is three-dimensional, has colors, and the continuation of the story is that this person goes back to the cave and tells the others what he saw, and nobody believes him, and in the Greek standards, there is a fight. So that is the pursuit of the truth, but the pursuit of the truth is something that people have in different ways. So there are people who do amazing experiments, that they try to understand nature and the atom. After all, we are here in Demokritos. And there is another way to pursue the truth, and that is through theory. And that's what people have done over many, many years. And unfortunately, I will not talk about the Greek, I'll talk about the German, who I believe was the initiator of the computational thinking. And he was the first who thought that, you know, if you have philosophers and philosophers are arguing about one thing or another, maybe one day there will be a quantitative way to settle all these disputes, and that is the calculemus, let us calculate. He thought that there is a way of doing these computations. So computing has a history, and the history of computing is not very pleasant. What you see here is two people that maybe you have seen recently also as movie characters. One is von Neumann, the other one is Oppenheimer. And computing began with this. Computing began, unfortunately we don't hear the sound, computing began by devising machines that would create atomic bombs. And again, you don't hear this guy here talking, but what he says, this is from 1963 or 64, 61 even, and what he talks about the imminent rise of computers, and that computers will be as dangerous as the nuclear bomb. I'm sorry, I don't have the sound. So computers have evolved over the years. This is my personal history with computers. This is 1981. You can tell my age. That's when I entered the National Technical University of Athens and had access to cards and other things like that. And over the years, I was fortunate to touch, up to 1997, let's say, some of the major computers. After that, I became professor, and I didn't touch them anymore, but my students did. And we have been able to have access to some amazing machines, and these amazing machines have given us a unique perspective. I think there is no technology in the world that has magnified itself in terms of its capacities by a factor of 1 trillion. And if you think about it, take any measurement you want, you can go from the nanoscale to the stars, then you can understand what does it mean that before we were only able to observe something very close to us, and now we can go very far and observe it at the stars. Computers is a major power, and that actually is what has been shaping a lot of the technology of our times. So what we have been doing in my work is we have been looking into developing solving flows and forecasting flows and analyzing flows at the nanoscale. This is a carbon nanotube array, and we put water through this. We have been studying blood inside microfluidic devices to detect cancer cells, and we have been conducting macro-scale simulations of shock bubble interactions. And I take the privilege of showing you some of the simulations that we have been doing. Again, what is the way that we use computers here is we take equations, here the Navier-Stokes, we solve them, and we try to do forecasting of different phenomena. And here, for example, you can go from simulating waves to simulating microfluidic systems. Now, this way of doing things has a limitation. There is a certain number of bubbles that you can resolve. It's not possible to resolve the oceans and the atmospheres and the climate. So over the last 40 years, there is a line of work where people have started to think, is there something else that we can do with computers? And I think Vangelis mentioned that at the inception of the Institute of Informatics, Institute of Plηροφορικής, here in Demokritos, people thought, what if I use artificial intelligence to study patterns. I happen to think something similar about 35 years ago when I was a postdoc at the Center for Turbulence Research at Stanford University. I attended a course in computational psychology by David Rumelhart. David Rumelhart is the founder of the backpropagation algorithm. And that clicked for me because I realized that you can take patterns and do pattern recognition, but perhaps you can take this pattern recognition and apply it to the forecasting of complex systems. The reason I'm showing you this is because I want to show you two papers that I wrote. One was wrote in 1999. As you see, it has been published in the proceedings of the local place where I was because simply I could not publish it anywhere. And then a few decades later, I published this paper, has over 2,000 citations. It's a review article. Both are review articles. They describe some of our work, so I recommend you look at that. And what you see in between is the progress in computing power. The progress in computing power, this is the most powerful supercomputer in the world up to 2019. This is the number 500. This is the total capacity that we have. And I want you to appreciate that when we were doing machine learning back in 1997, if we had access to supercomputer, and we did, it would take us 1 year to train a neural net. And today, training the same neural net will take 3 or 2 minutes. And that makes a big difference. That makes a big difference in how you think. You start make a big difference in the kind of mathematics that you do. Of course, computers were not so popular with the public until eventually one of them beat a human. They beat Garry Kasparov in chess. There is the legend that the Deep Blue beat Kasparov because of a bug, but I will not dwell on that. Computers have been well capable of beating us in many other things that we have been considering the landmarks of intelligence. And what has been important about this is that the public became aware that there are computers who can do tasks that everybody could relate. Perhaps not many people can relate with simulating bubbly flows, but you can relate about playing poker, chess, or the game of Go. Now, of course, this led to an onslaught of different publications and different statements. You have all the most powerful and the most intelligent people talking about AI, and some of them consider AI to be a big existential threat. There is another people that think that is a transformative power. And with all this, I would like, if you allow me, to tell you my personal view. That is something that I read somewhere, and unfortunately, I never recall who wrote that. If you find it, please let me know. That the best place to see the world is not the bottom or the top of the mountain, but the side of the mountain. And I would like to take this perspective when I talk about artificial intelligence as well. And this does not mean that the side of the mountain is a bad side, but there is an upside and there is a downside, and I think having a perspective is always important. So now, besides artificial intelligence and all these existential things and how it can change the world, there's a lot of people who make money with artificial intelligence. And then there is this beautiful book that is done by economists, which talks about prediction machines. And what this book says is that computers have made arithmetic chip. You can calculate millions of numbers. Solving more equations is done more easily and in less times. Either you solve it by discretizing and doing numerics or by doing AI. And so the key question is, what will AI technology make cheap? This is prediction. We can predict. Prediction is central to decision-making under uncertainty in particular, because you can calculate risks. And if you have better prediction under uncertainty, there is new opportunities for all companies. So there's a lot of money to be done by being able to forecast the climate, by being able to forecast the economy, being able to forecast when it's going to rain or what crops you should plant. But at the same time, there is another sobering thought that people say, okay, there is all sorts of information technology that's going to change the world. But I want you to see that this is taken by a US government site, that the annual average growth rate of productivity is stuck, and we don't progress as much as we claim or we like to progress by information technology or AI or other things. So I think Something else may be needed, and I'm not sure what it is, but I hope this workshop can help us appreciate the different perspectives. So we talk about artificial intelligence. So what is artificial intelligence? Of course, many people can have different interpretations about what is artificial intelligence. I very much like to bring up John McCarthy, who is the person, is a professor at Stanford University, and who is the person who coined the term artificial intelligence. So over the years, there's people that talk about the definition of artificial intelligence, and usually, as you see, they relate it to humans. They relate it to the way humans think, as Bellman does here, and he talks about the automation of activities that we associate with human thinking, and I stress the word automation and the word human thinking for solving, decision-making, and learning. And then there's the other part that perhaps our friends in robotics would like to pursue, which is to act like humans. And the idea is the study is how to make computers and other devices do things at which at the moment people are better. There is another way of going about that, which actually I want you to see that there's the way humans think, and then there is the rational way of thinking, because very simply what I allude to is that humans are not always rational. So the idea is that you can think rationally, which is that you take the study of computations, that you have perception, reasoning, and acting, or that you are acting, rationing in terms of a study that fails to explain and emulate what we are doing after all, and not only what we may be having in our thinking. So there is a lot of different ways, but I want you to see the two ways of thinking like humans and thinking rationally, and there is a lot of questions about the human mind and whether the human mind is what artificial intelligence should be trying to emulate or try to replicate or to replace, if you like. And there is a lot of issues that people talk about. Perhaps some of you may have watched the American presidential debates, and maybe you have made some thoughts about what is a fact after all. So it seems that the human mind needs help, and it seems that facts don't necessarily change our minds, and it seems that we are driven by some kind of an evolutionary pressure to survive, and we are using our words and facts in order to overcome our adversary, in order to overcome the person who has a different opinion than the one that we have. And at the same time, there are other people who argue that what sets us apart is what we are doing right here, perhaps in a one-sided way, and what sets us apart is that we talk. The fact that we go out to the Café Neo and we talk with our friends, this is intelligence. And the fact that we exchange with each other, this is intelligence. And I'm a big believer, personally, that the way, if intelligence is to emerge, is through some kind of interaction, not only between us, but with a proper interaction that we can have with computers. There is a lot of papers that are pointing to this direction. I just picked one. This course is going to tell you about LLMs. I believe Ionas, Yanis Asael, and others are going to tell you about large language models. And there's something that seems to be emerging with all this research in computation, that these computers and the large language models, they start to have cognitive and metacognitive capabilities. So the argumentation that we should interact with them as equal partners, as partners from which we can learn, I think it's an important aspect of what's going on in AI. Let me go back to John McCarthy. And again, I hope you have heard from me by now that I insist on the part of computation. So what John McCarthy defined as intelligence is the computational part of the ability to achieve goals in the world. And I want you to pay attention to every single one word that he says, because in particular, it's not about the system having a goal or not. This is not a property of the system, but it's how we perceive the system. We are the observers. That's how we perceive the system, what it does. You can consider the system an animal, an object. How we interpret the animal and the object, these are the things that we ourselves are perceiving and defining as intelligence. And the other thing which is very, very important, because it kind of challenges the way we are doing science. Maybe the dogma that I have heard and my generation have heard is for many, many years is that we do science in order to understand. And after we understand, we are able to create and to extrapolate. But I think there is another way of doing things. The other way of doing things is first you do, then you go back and you understand. Because perhaps the things that you have understood have no relevance when you start interacting with the system and you're pursuing the behavior of the system. So according to John McCarthy, the system is better understood, predicted, and controlled in terms of the outcomes, not the mechanisms. And that actually points to another feature of AI, these black box capabilities that very often people from other scientific fields find as dismissive. Oh, black box, we don't understand, it's not important. It's very important because you have a system that is able to do things that maybe we don't understand, but the system itself is capable of achieving. Now, besides artificial intelligence, the generation of John McCarthy didn't take this very far, because they started to talk about logic and other things. But I think the place where deep learning had one of its big bang moments was this paper, the ImageNet classification with deep convolution and neural networks, where people were shown to outperform everything that was out there in terms of pattern recognition. So I want you to pay attention to the three names: Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton. Do people know where these people are today? Yes? No? Tell me. Oh, who is in OpenAI? Very good. We'll come back to Ilya. So now, this capability of doing patterns has expanded. It's not only about random images, but it's actually useful images. People started to use images in order to detect cancer. And also, there's another thing that AI or machine learning has started to do. They start also to replace lawyers, if you like, by doing things in seconds that it takes them thousands of hours. The study can continue and can go on, but I want you to be aware that because of computers, because of devices that can record signals, we have another amazing resource in our hands that it's almost accessible to everybody, and this is data. We have billions of devices, and these billions of devices are propagating not only to the Western world, but also to the rest of the world, where there is even more population and there's going to be more and more and more data. So this is something very, very powerful that is happening. So the question is, we have problems and we would like to solve them. And one can perhaps think of two ways of solving problems. One way of solving problems is by classifying problems in terms of the availability of data and in terms of having first principles. By first principles, I say physical laws. We know, for example, Newton's equation of motion. So if you take the different fields, engineering and physics has been traditionally rich in terms of principles that we're using to solve problems. And there's other places like doctors and medicine and social sciences and finance where they are more data rich and less about having equations that they're trying to solve. And there is a place where there is no data and no principles, and that's where you find lawyers and experts, and that's why we pay them all the money that we pay them. Of course, there is more of a move of engineering and physics to the data-driven world. And now comes a statement that I want you to think and tell me if you agree. So how do you go about solving problems? Well, you use lots of training data and a big, deep neural network, and success is the only possible outcome. How many of you believe in this statement? You believe, and you're Kostas who talks after me. Very good. Anybody else who supports Kostas? You don't believe that? Even if it is this guy who tells you that? Well, you know who's this guy? Well, this guy is Ilya Sutskever, from the co-founder of OpenAI, and he has proven to you, has proven to all of us that with a lot of data, you can get ChatGPT and you can actually solve problems. I'm not sure how many problems and what kind of problems, but this is not a trivial statement, and it has to be taken seriously, because one of the things that you will hear about in this lecture series is going to be about foundational models, which are actually changing the way that we go about solving problems, and we go away from first principles, and we start taking data and machines and try to solve problems. And I will not talk much about that, but I find amazing that you can take things that usually we as humans had access, text, images, can go to libraries, we can talk to friends, we can have all sorts of 3D signals, but we don't process them as fast as a computer perhaps would process them. And what is amazing that computers can process them, and then you can ask them in a particular context. You can ask ChatGPT about what is the best restaurant to have seafood in Athens, or you can ask ChatGPT to tell you some medication. Both of these things I need, actually, but it's ChatGPT that is able the same thing to give you, and that's an amazing technology. As I said, I don't have time to talk very much about my own work. I'd like to tell you there is a lot of roads that are being less traveled between AI and computational science. There is a little commentary of 2 pages that I will share with all the participants that I wrote that describes some of our work and where I think the computational science people who have been thinking in terms of principles and the AI people maybe have common paths that they can pursue. And I would like to also tell you, again, looking forward to what may happen in the future, I'd like to copy something that is called the ladder of causation by a person that I like very much, Judea Pearl, and his book, The Book of Why. So according to Judea, the humanity is climbing a ladder, and this is the ladder that he calls the ladder of causation. And at the bottom of this ladder, there is the possibility of making associations. And these associations are often related to things that we see and we observe, and perhaps at this level is where you can put the machine learning and the pattern recognition capabilities that we have at the moment. There is a second level where we start to interact with the systems. When you have babies that they want to see if something breaks or something is hot, they push it or they touch it, and then by intervening with the system, then they realize what is this particular system doing. And this is very much consistent with what John McCarthy was talking about, a system not being understood in terms of what's inside, but on the ways that you interact with this particular system, this intervention. And according to Judea, there is a top of the ladder that only humans occupy, and this is the place that you can have imagining, retrospection, and understanding. This is the place that you can have counterfactuals, and according to what Judea wrote, this is the place of imagination that humans will occupy and machines may not. I think that perhaps we can agree that one of the places where imagination is important is in doing mathematics, and perhaps many of you believe that mathematics is something that only humans can do. Well, I was very honored to be part of a committee of the national academies in the US that looked how artificial intelligence is changing mathematical reasoning. And I can tell you that mathematicians themselves, famous people like Terence Tao and Yann LeCun, are thinking that artificial intelligence actually is slowly arriving and knocking on the door of imagination and thinking that has been reserved only for us humans. So there is a lot of exciting possibilities. And what I would like to say is that AI is one thing, computing is one thing. Don't forget the computer we have in our brain and in our soul and in our guts, and I call this thing thinking, and I think you can take all these 3 things and use them for X. And X are the big problems that our generation and perhaps your generation even more is facing. You are facing problems of energy. There's going to be issues with water. There's going to be issues with poverty and inequality. And of course, system complexity is something that is problematic. So the future may look like something like that. And I think computers are here to stay. As Vageli said, we have to consider ethics. We have to consider thinking. We have to consider how philosophy is coming together with AI. And what I find amazing about AI also is that in the old days, all the sciences, if you think about Plato, Aristotle, Da Vinci, Galileo, and Copernicus, all these different philosophers and scientists, they were able to traverse different scientific fields. At some point, different scientific fields were separated. I find AI as a very beautiful conduit that connects different sciences, but in this conduit, we should never forget that it's also computing and human thinking that connect these sciences. I would leave it at that. I have nothing more to say. I think it would make no justice to our work if I go to any of that. I would like to thank you, and I'll be happy to take any questions or have discussions about any of the topics that I presented. Thank you very much. Sure.
So this was very inspiring. Thank you, Petro, very much. You said it's a personal opinion, and it's very subjective, I think you tried to reveal. But you never told us whether you believe what HIAS is claiming.
About HIAS' claim, in this case, we have to put back HIAS' claim. I would only put in parentheses up there the word some. Because indeed, I think some hard problems, that's the way to go about them. Don't ask me why that's the way to go about them. But I think for some hard problems, foundational models have already shown that this is the way to go. And I can tell you why other methods, the methods of first principles, are not capable of doing that, because we're running out to the limitations of the numerics the way we understand numerics today. And that's not the way of solving complex problems by using equations and discretizing them in the computer. But if there is a way that you can combine perhaps this way and the way of thinking of first principles, I think that's perhaps is a better way to try to expand on a broader array of problems. And this article this commentary that I wrote for Nature Reviews Physics alludes to that, alludes to this interface between AI and computational science and the classical thinking that we have. But for some problems, and I think the success of these methods speak for themselves.
Some is interesting, but it's not quantifiable. Do you want to say whether it's the majority or the minority?
I don't think I'm capable or knowledgeable enough to answer this. I don't know. I think in the end, the person has to come and say, what is the question that we are asking? Okay, so if the question we are asking is how to make profit, then we have to think if what we have at the moment and what these methods present us are suitable for making profit. If we are to cure cancer, you again have to go and realize that perhaps we don't really understand how cancer works and we don't really have a cure. So why not try that? If you start to think about inequality, here's another one that you can start to think that AI and computers are going to be for the privileged societies, and maybe other societies would not have that. And perhaps AI can lead to further inequality, and further inequality can lead to ugly situations that are becoming important for our social structures. So we need to think, we need to understand AI, not to see it as an enemy, not to see it as a foe, not to see it as a monster that threatens human existence. We have to understand the mathematics of AI. There is people who talk about Bayesian inference and how to integrate data and models. There's a lot of different things that I think we need to take into account. Foundational models is one way, but perhaps not the only way. I don't answer your question, but all I want to say is I wish I was on the other side of the classroom. I wish I was 23, because there's an amazing thing of things that are happening, and you are very fortunate that you live in wonderful times, and you have wonderful capabilities in your hands.
I would push you further, but maybe somebody else wants to ask a question. Yeah, the lady over there.
Yeah, thank you so much for this really amazing vision. What is your view of how do you estimate capability of AI to solve any of the, truly first principles, like the 23 or 25 Gilbert's problems? Is there any chance, or?
Well, I don't know the 23 or the Gilbert problems, but I know these millennium challenges that people have put forward. There are people, for example, in something that is very dear to my heart, which is to study the singularity of the Navier-Stokes equations. And so far, the classical way has not been very effective in identifying even a singularity in an equation that we came up with. And I have the feeling that AI and machine learning are knocking on the door of this particular problem. There is AI that starts to do geometry, and this workshop on AI for mathematical reasoning, it became clear that perhaps AI can even copy the mind of Terence Tao and try to solve problems the way Terence Tao will go about doing that. And he can take the brain of Terence Tao and the brain of Yann LeCun and try to combine them and do other things. So I think it's a research that is worth pursuing very much, because if we care to answer the Gilbert problems, which I don't know that they are, but I trust you they're important, I think we don't have many solutions. We have reached limitations with existing methods, and this AI presents a new way of solving problems, which I think is very valuable. But not alone, I insist on this.
The guy over there.
I would like to ask if set theory, as a part of mathematics, plays any role in data sciences. For example, because I did some data science course through MOOCs, I remember that when we have classes of data and we need to find the syndroids between them, it looks like two sets. Is it how it works in data processing? I mean, about set theory.
I'm not sure I know. I don't know how machine learning applies to set theory. I think I'm not capable of answering this question.
Oh, okay.
Perhaps one of the speakers in the following sessions would be able to answer that. I don't.
Okay, thanks.
There was another hand.
Yeah. I wanted to ask, you briefly talked about what doesn't AI have in contrast to humans. Since AI works mostly with information we give it, also patterns and everything at least the developer or the human gives it, I understand that it's way contained to the information provided. So will it ever become to a state where it's actually going to be able to create new information, meaning that, okay, well, now I don't provide it with something else, something new, something well already established. It just innovates something extremely new. So will it overcome in a way that containment of the informations that are being given to it?
So this is a question that I have myself, and I have heard it in several conferences. So I'd like to give you a summary of all the different things that I have thought about it and what I have heard. Indeed, you're right, in particular when you're talking about supervised machine learning. When you do supervised machine learning, you have some data, and you have a machine that tries to match this data. And basically, mathematically, what you do there is you're minimizing an expectation over a probability distribution of the data that you have given to the machine, okay? So very fairly, you can say, well, the machine cannot extrapolate beyond this probability distribution, and indeed, this can be the case for supervised learning. There is a particular example of something called the elephant in the room, where people give to a machine a lot of images of a living room, and it's able to classify humans, couches, etc. And then all of a sudden, you take a little image of an elephant, You stick it somewhere artificially in the image, and this thing starts to freak out and does not even know what is a human and what is a chair and all these things, and that's why it's called, it's a paraphrasing of the classical statement, elephant in the room. So this is about supervised learning with a little caveat that I will put on there, that you don't necessarily know or we understand all the patterns that is inside this probability distribution. So you may as well discover things that you have not initially thought about or considered and just simply exist inside the data. And because they exist inside this data, machine learning is well capable of finding this that we are not. There is another part of learning, which is the semi-supervised learning, and which is something that is close to my heart, and that is the reinforcement learning, which actually I'll take a second to show you. So reinforcement learning works with less data, if you like, and works with another set of principles where you have a stimulus, an action, and a reward. And the set of stimulus, action, and reward is something that many of us do, in particular when we are young. But there is an example that we have here that is given by one of the pioneers of reinforcement learning, who was a zoologist, and he was Burrus Skinner, and who was at Harvard zoologist, and who was teaching pigeons to play ping pong. And the way he taught the pigeons is by opening a door down here, and whenever one of these pigeon scores, when the ball will cross, the door will open and this thing will eat. So he had taught pigeons to play ping pong, if you like. So you may think that this is all crazy if you first see it, but things like that I think can be automated for many other processes. There is an interesting story. Do people know about these experiments? About the pigeons? Do you know why he used it? Burrus Skinner. So he was financed by DARPA, and the idea was, you can read all about that in Pigeon Pilots. The idea is that you create missiles, and it was the time of the Cold War. You put the pigeon inside the missile, you train the pigeon whenever it sees a particular landscape to press on a button, the missile goes down and bombs the area. I don't think they applied that, but this is reinforcement learning, and reinforcement learning, I have seen it in my research, outperforming humans in a task which is something which designs airplanes and cars, which is turbulence modeling. I will not talk about that here, but it's able to figure out patterns with the proper training. You always interact. In reinforcement learning, if you are not careful about what are the states, the action and the rewards, you're never going to find a causal relationship. But if you start interacting with the system and you start playing with that, you find wonderful things that one has never seen before. And back to whether we can innovate. I will give you a provocative statement that came out of this AI workshop, and it came out from mathematicians, and that the mathematicians themselves, they say, that AI may produce mathematics that ourselves may not be able to comprehend or to process when it is being produced. And so we have to keep an open mind about what we call innovation and what AI may call innovation, and find the ways to meet.
Thank you very much.
Thank you.
We have time for one last question. There was one guy close to the guy with the black shirt. Was raising the hand.
Do you think that these systems that we understand based on their outcomes and not their mechanisms are humanity's glimpse outside Plato's cave, or just another shadow?
How much time do I have? It can be another shadow. It can definitely be yet another shadow. Nothing tells me, I have no proof to tell you that this is the end of the story, as this is not yet another shadow. In fact, I would like to think that this is just another shadow, and the future has a lot more other exciting direction for you to pursue and to discover.
Thank you very much. I think we'll stop here. Thank you very much, Petro.
Thank you.